Welcome, everyone. We just heard an excellent ITC colloquium by Evgenya that many of you know. She looks very familiar to most of us. And she will tell us some more in a few minutes. Before I mention the other presentations, I just wanted to alert everyone that we would have on May 9th and 10th, we will celebrate 20 years for the Institute for Theory and Computation, the ITC, that this lunch is part of. And over the years, we had exceptional postdocs that now became leaders in their field, and they have tenured faculty appointments at many distinguished universities, prestigious universities. So anyone in this room or elsewhere within the CFA community is welcome to attend this conference on May 9 and 10. And the talks will be at the Hilles Library, and there will be a banquet on the first day, which is Thursday, May 9. It will be at the Sheraton Commander. So to register, you can just scan the Q code on the announcements that are within the corridors here, or you can contact Jacqueline Donahue right there, and she can help you with the registration if you need any information. We definitely have room for anyone interested as of now. So please register. It's just 3 weeks or 4 weeks? I guess
About
4 weeks. 4 weeks. So 4 weeks from now, so now is the time to register. It promises to be an exceptional meeting, and also opportunity for many of you to meet faculty at other places. If you are thinking about applying for jobs, this is a good way to connect with a collection of leaders in many different disciplines. It's a very diverse community in terms of interest. Okay, so the other speakers today are Igor, also very familiar to all of us. Where is Igor? Igor?
Igor Uber was late.
Oh, he's late. Okay, so let me try and pronounce his last name. Chilingarian. I hope I did
Pretty good.
Yeah, okay. And he will talk about baryons and dark matter in the largest disk galaxy in the universe. Now that sounds quite remarkable. The largest disk galaxy. And then we'll hear from another local person, MJ Park, it's over there, who will talk about star formation and quenching histories of massive quiescent galaxies at cosmic noon, revealed by JWST NIRSpec. And finally, we'll hear from Elettra Piacentino, right?
Yeah.
Also local. And she will speak about photodegradation of small aromatic isotopes. We'll start with Evgenya, who will talk about a new project, SPARCS.
All right. Is this on? Can you all hear me okay? Yeah. Okay. Fabulous. Well, so great to be here. I absolutely love this format. So thank you to the ITC folks for organizing it. In the talk that I gave just an hour ago, I went at length as to why we care about the high energy radiation environment of exoplanets, particularly the UV radiation. And so one thing that is important to note is that we do not have enough data. HST is just not enough to provide the UV information that we need in order to understand exoplanetary atmospheres, their photochemistry, their photoevaporation, and their evolution, and also their formation. So we, a few years ago, proposed the SPARCS mission. It's the Star-Planet Activity Research CubeSat. And I can honestly say that I have never put an exclamation mark before in a title of a talk. But I did because I'm actually very, very excited about it, because we're in a very exciting time. You know, for those of you who might have been on mission proposals in the past, you propose and then you win and then you go through the development stage. And we're now really at the tail end, where we have the pieces in place, we have a devoted lab, a dedicated lab, we're putting it all together, and we're going to deliver it soon. And so this is a very exciting time for us. So what is SPARCS? In short, it is a 6U CubeSat, so it's not very big, about the size of a family-sized Cheerios box. It is funded through the NASA APRA program, that's the Astrophysics Research and Analysis Program. It was the first program in NASA to fund small satellites with 3 explicit goals. One is to do excellent science. Second is to be a technology demonstration for technology that is relevant to bigger missions like mid-X's and flagships. And 3 is to train the next generation of mission leaders, because not just PIs, but I mean leaders, because there are many leading roles, and I would argue that everyone on my team is a leader in their own way. So SPARCS achieves these 3 things. Here is our team. It's not too small, but it's not too big. We have a science group, we have an engineering group, the camera is coming from JPL. Of course, we have project management for anyone who leads missions or any project of a certain scale. You wanted a dedicated project manager. All the names in green are our postdocs and students, because we do need to train people for the bigger missions here. These last 4, so we have some graduate students and postdocs. These last 5 here are our interns, and we actually turn over our interns every year to give undergraduate interns experience in the lab. Our technology mission is to fly these new detectors invented at JPL. They're called these delta-tope high quantum efficiency detectors. And so JPL built our camera. It's called SPARCam. And what you can see here is the throughput, the total throughput of the system is about 5 times NASA's last dedicated UV mission, GALAX. And that helps us gain back some of the sensitivity from what is otherwise a tiny little telescope. Okay, you can't tell from here. There's an image of our actual telescope. It's 9 centimeters in diameter. Okay, so it's very small, but it's totally devoted to one experiment, which is exactly what these small sats are so beautiful at doing, is you can do one experiment really well. And so this is our light path. You see the light comes through. I do have a pointer, actually. Here we go. The light comes through the telescope, and it hits the dichroic. And then the light is split into 2 bands, the far UV and the near UV. These are, I explained previously as to why these are really important wavelengths for understanding exoplanet atmospheres. If you are curious to hear more about that, we can talk more afterwards. And as Avi said, I'm around here and I hang out in P350 if you want to come find me. But the main goal of SPARCS then is to measure not just the quiescent flux, but so the quiescent flux meaning like the basal normal level of flux, but also the flares, because there's a ton of energy coming out of the flares. Here's one example from GALAX that shows a flare that increases in near UV photons by a factor of 9,000, right? So one flare in 200 seconds goes off by a factor of 9,000, and we've been learning through limited HST data how often these low mass stars actually flare in the ultraviolet. So here's a simulated light curve of what we were going to be doing with SPARCS. Using real flare frequency distribution, so real flares from stars, we're able to predict what we're going to be looking for. So we're going to see both the quiescent, which is down here, which is modulated by the rotation period of the star, and we're going to see the flares superimposed on that. And our goal is to spend almost a month on every target. Okay, so a month of time. And I'm showing you here the longest HST stare on a single target was on Proxima Centauri, and it was 36 hours. Right? And my group and I, we've had 2 large HST programs with a total of about, I would say, 10 days of HST time overall, right? And that's still a ton of HST time, but not enough to get the flare statistics that we want. What we've learned from HST is that young stars flare very frequently, right? Much more frequently and much more energetically than old stars. So this is good information. We're trying to understand the evolution of exoplanet atmospheres, so we need to know what's happening when the planet is both young and when the planet is old, right? Because most of the planets that we're observing now are actually old. So what was their history? And it's really anchored by this daily flare, this thing called Has flare. We call it the Has flare. It holds the record as the strongest M-dwarf flare detected by HST. And it happens every day on a young star. This is an increase of a factor of 200 in the far ultraviolet. Okay? So what we don't have is the information of what happens to the stronger, rarer flares. And the main reason is we just cannot stare long enough. HST will just not give us a month or a year to look for these really big whoppers, right, that are absolutely doing something to the planet. What exactly is doing depends on its energy and the planet and all sorts of things, but we really need to get to this point, and this is where SPARCS really shines. We're going to be probing these really strong flares that are just more rare than these weaker flares. And we're going to be able to stitch this over and wonder, does this line go on? Where does it turn over? Clearly, you can't have an infinite energy flare. It's got to turn over at some point. And individual targets that we'll be staring at for 1 month. But then the whole mission you can combine, because we're focusing on low mass stars exclusively, we can combine the data and do some statistics of the kinds of flares we want there. Where is SPARCS today? Well, it's in this lab in the basement of our building at Arizona State University. This is our graduate student Logan Jensen and our engineer Nathaniel Struble. And I took this picture from the window a few weeks ago because it's the kind of lab you just don't let the PI with their grubby little hands get in there, and so they don't want me in there. So I can just take this picture. But you can see this is our structure, our support structure for assembly and testing. Right now, it's in our TVAC chamber, thermal vacuum chamber, where we do the aligning, we're doing the focusing, we are doing a lot of testing in there to make sure that the payload, and by the term payload, I mean the telescope and the camera together, are being tested. Now, we're waiting at the end of this month, on May 1st, our spacecraft will arrive from Blue Canyon Technologies, and we will start the integration of our payload with our spacecraft and do the same kind of, redo the testing, the vibes, the thermal testing, all the things that you need to do for NASA to let you fly your mission. Let's see. So where is SPARCS going? SPARCS is going to be launched into a sun-synchronous terminator orbit at around 600 kilometers. And what that means is that we hope to be launched to a place where we're always looking into deep space, the telescope, and the solar panels are always facing the sun. So this is like maximum power, also maximum observability of your target, so you can have as much continuous observations as you possibly can. The request for proposals to the launch providers went out this week, so that's very exciting. The spacecraft from our side will be ready by the end of this year, in just about 7 months, if all goes as planned, which, you know, nothing really ever does. But that's the plan, and then we will be waiting for the right launch. And this is what happens with small satellites, typically, is you're hitchhiking a ride into space. And so you have to go when your launch goes. And so we've made this criteria that we need. We need 600 kilometers or higher. We want to be in a sun-synchronous orbit. We need some cleanliness issues because UV is very contamination sensitive. But after that, then we wait for our ride. And so we're hoping for something in early 2025, so within a year from now. But if we have to sit on a shelf for a few months, we sit on a shelf for a few months, and that's what you have to do. So to summarize the key specifications for our design, as I said, it's a 6U CubeSat, sun-synchronous orbit, 2 UV bands. We have a large field of view, a relatively large field of view, 0.7 degrees, which means we have lots of other stuff that we can observe. Any other UV interesting and variable targets, we will be downloading as well, and that will eventually be something that we can open up to others. And we will observe roughly 20 low-mass stars from 5 to 40 days per star. Thank you very much.
Let me ask you the few trillion-dollar question.
Let's hear it.
Our sun, every now and then, has an eruption. And the Carrington event, about 150 years ago, if it were to occur today, then it would cause damages to our infrastructure at the level of trillions of dollars. What is being done to alert or predict maybe when the next one?
Oh, for the sun, can we predict? What you want to know is, can we predict coronal mass ejections from the sun?
Well, not so, yeah, but was it a simple coronal mass? I mean, it was an energetic event.
It was an energetic event, probably a CME. What else? What is more energetic than a CME?
But we now have infrastructure that we didn't have centuries ago, and therefore the damages would be huge. And I don't know if I mean, obviously, when something like that would happen, there would be a lot of money dedicated to research because it will cause so much damage. But
Right.
are we smart enough to, do it before it happens?
It's an active. There are dedicated NASA heliophysics calls for grants for people to work on exactly this problem. People are definitely aware of our technological assets in space. There are multiple actual programs. One of them is called Living with a Star, which is very much devoted to this. What does it mean to live next to a star like the sun? The good news is that if they're correlated with flares, the way I showed earlier today, then if you see a giant flare, you can predict that maybe a CME is coming, and CME takes time, right? So the light travels at the speed of light, but the CME travels at a few hundred or 1,000 kilometers per second. So you now have a couple days to shut your, you can turn off your spacecraft, turn the power down. Maybe if you have enough control over your spacecraft, turn it. We also shield, for another mission that I mentioned earlier, UV scope, we are planning a lot of aluminum shielding. So I see people are thinking a lot about how to deal with that. Yeah. 100%.
Please.
So I have, I hope your satellite won't hit any spy satellites that are all in the same orbit.
I hope so.
But, so my question is, recently, I dealt with UV, with the Indian UV Observatory, AstroSat proposals, and I always struggle to understand what is the main reason for the loss of efficiency in the near and far UV. So why is the effective surface area so small? Even for Hubble, it's like a couple of thousand square centimeters.
Yeah, that's a very good question. Why is it so hard to do the UV? The inefficiency comes in multiple ways. One is, of course, in the reflectivity of your mirrors. Like the efficiency can be 4%. Right, so if you have a lot of bounces, right, so you're trying to fold your light, right, feed a spectrograph perhaps, whatever you're doing with it, every one of those bounces is potentially a huge, well, it is for sure a huge hit. So one of the CubeSats that NASA is launching, called Sprite, is going to be testing, one of their technology demonstration is to test new UV enhanced coatings so that you could have much higher levels of reflectivity and efficiency. That's probably, I'd say, one of the main reasons. Yeah?
What's the nominal lifetime of the mission and extension possibly?
Great question. What's the lifetime of the mission? So we are currently funded for a 1-year mission. If all works well, then we could apply for extended operations time and more science time, and that's an option, certainly. There is a rule now that actually was only implemented after we were already selected, that we have to degrade into the Earth's orbit within 5 years. So this is part of NASA's effort, or the government's effort, to get rid of the space junk. So that's another reason why we're limited to 600. We can't, if we got a if we got a ride to 800, we actually are not allowed to go there. It's 800 kilometers above the Earth and stay there for 50 years, right? Because we are required to deorbit in 5 years.
Okay, last question. Go ahead.
What keeps you up at night? What's the biggest risk profile for you in this mission?
The biggest risk right now, well, I'm happy to say that all the risks are dropping down as you get the hardware and doing all the testing. The biggest risk right now, I think, is contamination. UV is very, very sensitive to contamination, and if the spacecraft launch provider cannot provide a clean environment for us, then we will be flying with lower sensitivity than we're predicting.
Okay.
And because I'm not in control of it, that's why it keeps me up at night.
Let's thank you again. I also wanted to mention that we have the privilege of a distinguished visitor who graduated from the program here a while ago. And he also is now fostering a relationship between Harvard and China, so he's leading those in there. And what was your PhD about?
Actually, I started with solar physics with the Baryons, and then worked again with the
All right. hear me?
Yes, do you have the mic?
I'm not sure.
There's a little switch on the top.
All right. Now it should be better.
Yes.
Okay. All right. Okay. Hello, everyone. So this time I'm not gonna talk about intermediate mass black holes, neither about ultra diffuse galaxies, but also about something diffuse. This will be the giant low surface brightness galaxies, and that's actually a painting by the PI of this project, Anna Saburova, who did it like demonstrating. This is Malin 1. This is her view of Malin 1, the first prototype of giant low surface brightness galaxy class. And we are talking about one of those very unusual galaxies that we discovered just a few years ago. So what are these giant low surface brightness things? They were prototyped by Malin 1. Malin 1 was the first object discovered in 1987 in the direction of Virgo cluster, and actually this part was visible in Palomar plates, and this has the size of Andromeda. But this enormous disk with a radius of in excess of 100 kiloparsec was discovered only in the late 80s. These galaxies are H1 rich, and they're slowly forming stars. They're low surface brightness cousins to so-called superspirals, which were discovered relatively recently, like enormous spiral galaxies. Their dynamical masses are well in excess of 10 to the 12, and so they're expected to have rich merger histories featuring major mergers. If you look at any numerical simulation and look for 10 to 12 solar mass halo, you'll discover that most of them are supposed to be formed by major mergers. However, mergers tend to overheat and destroy disks. And that's the mystery of the giant low surface brightness galaxies. So we're trying to understand how they're formed, and they also work as stress tests for cosmology and for our understanding of galaxy formation in general. There are several scenarios: slow gas accretion from cosmic filaments, minor mergers with many dwarfs, so you basically build up this disk gradually, or major and plane mergers, which can preserve disk and make it bigger. There have been only a few of them known until recently, and Anna published this beautiful paper a few years ago, the in-depth study of 7 giant low surface brightness galaxies here. Here you can see the insets, and actually most of those were classified in the past as ellipticals or lenticulars, because you would never see these faint filaments that in fact are all rotating. So for all these galaxies we have H1 fields from the literature or from our own observations, and they all rotate at pretty high velocities. So these systems are really following the trend set by normal disks. If you plot them on the Tully-Fisher relation, that is the rotational velocity and the baryonic mass versus rotational velocity. And their disks follow the trend set by smaller low surface brightness systems, and they're just at the very top. So they have radii exceeding 100 kiloparsecs, while their bulges are sort of normal. They're kind of oversized, but well, not too much. They also tend to have 2 light central black holes. That was revealed recently by multi-wavelength observations, because some of them, the statistical frequency of having an AGN in those systems is higher than normal. And they normally live in poor environment, except for instance this one. There are a few exceptions. 2 of those were discovered to have counter-rotating gas with respect to the central bulge, which is sort of an indication for an external origin. But the main conclusion of our paper were the diversity of origins for these systems. So basically, all the scenarios I mentioned might have been in the game. So we need more of them to draw solid conclusions about their origin. So why don't we use the automatic search, like to use an artificial neural network and apply machine learning to look for them? The answer is very simple. Well, machine learning is very efficient in detecting similar features wherever you want to find them. The sample size at the time we started this was only 10 objects, and so it was too small to train the ANN.
And simulations do not provide synthetic images that are realistic enough. So we went the hard way. We basically we scored 120 square degrees of Subaru fields using legacy survey interface. And 4 of us did it independently to remove the subjectiveness as much as we could. And we found 37 giant low surface brightness galaxies in the redshift range between 0.02 and 0.1, so at low redshifts, with the radii exceeding 50 kiloparsec. And this gave us the first ever done volume density estimate for those systems, which turned to be in a pretty good agreement with Eagle simulations. So unfortunately, the low surface brightness part here is gone. It's basically like you're looking at the Sloan Digital Sky Survey image, but because that's a projector effect. However, you can see here that the bright light profiles for observed galaxies for models were pretty much consistent. So the problem is that scoring through these legacy survey images became a real addiction in our team. And so people started just procrastinate using this. I guess it's better than watching cat videos, but still, it takes lots of time. Since 2020, we found 100 giant low surface brightness galaxies, including some very interesting ones. Once in early 2021, this source appeared. It looked like an edge-on galaxy far in the southern sky, and the redshift in the NED indicated that, imagine, this is 7 arc minutes at a redshift of 0.038, which is 160 megaparsec. So the radius is well in excess of 100 kpc. We had a Magellan night at that time, and we confirmed its redshift right away, because I thought first this was a mistake. And it took just 10 minutes to confirm the redshift of the galaxy and of 2 satellites, and indeed it was a very interesting source. Then we got immediately a DDT time on Meerkat. That's an H1 interferometer. That's a radio interferometer in South Africa, one of the SK precursors. And also SOLT data that showed a plateau at 320 kilometers per second and this wonderful velocity field with a few times 10 to the 10 worth of H1 in this system. And this blob that actually has a tiny optical counterpart, it's alone almost 10 to the 10 solar masses. So the galaxy is rotating. It has a beautiful, beautiful kinematics. So we were able to fit the simple dynamical model and recover the M200, the halo mass of 12.6. So 4 times 10 to the 12. That is, yeah.
I never interrupt in the middle, but this one, if you take the radius, divide by 2 pi r divided by the velocity, wouldn't you get the Hubble time or more than the Hubble time?
I haven't checked this.
Yeah, I think it's the Hubble time.
Yeah, it might be.
So it didn't have 1 rotation in the Hubble time.
Well, that's it. So the R200 is 335 kpc. So it's pretty extreme thing. We went further. So this one is really well detected in Galax, even though it's a very shallow exposure. It's an all sky image. We did H alpha with Magellan. We also did near infrared with Magellan. We observed it with the HST, and it shows very interesting morphology in the center, indicative of recent mergers. It also has a near UV point source at the nucleus that is coincident with the radio source, and marginal X-ray detection suggesting that there's an AGN. However, this AGN is covered by the dust in the inner part of the disk. It's not like a type 2 AGN, but it looks like type 2 AGN because it's actually hidden by the dust. So we also got deep spectroscopy from SOLT. So the first one I showed was 45 minutes, like a snapshot. We did several hours, and we were able to measure gas phase metallicity, and it showed completely flat gradient. Now we also have Muse mosaic for this one, but it's still in progress because we're still struggling with the data analysis. The data reduction for such thing is almost impossible using standard pipelines. All right. What do we have regarding its properties? It's a little bit below the Tully-Fisher, so it misses some baryons, or we are missing them. I don't know. Maybe there's a lot of molecular gas that we just don't see. We don't have the data. And if you plot the metallicity gradient versus inverse disk size, there are all these low surface brightness galaxies and GLSBs in the top, well, which is the bottom in this weird axis, but that's how astronomers measure this thing. And it's right there at almost zero gradient. So several satellites, including a compact elliptical galaxy that is likely a tidally stripped intermediate-sized spiral, suggest that mergers likely played a role in its evolution. However, the disk itself is too massive to be formed by a few minor mergers. Either it had accreted the entire plane of satellites that were discovered recently around many galaxies, or the merger just ignited star formation in its pre-existing H1 disk. Can numerical simulations reproduce the formation of a system like PGC 75143? I don't know. Final question, is this a unicorn? And the answer is no. We already found one system that you see here. It's a high contrast image called PGC 3921 that has the same radius and almost the same plateau velocity because it was in the Arecibo survey. It's close to the equatorial stripe. It also has clumpy star formation. It's not edge-on, so you don't have this boost of surface brightness as you got from PGC 75143. But it's very similar. We also found a smaller analog with clumpy star-forming disk at a slightly, it's tiny, 80 kiloparsec radius and 280 kilometers per second in H alpha. So many more will come with LSST. And before I stop, that's just an announcement. 3 team members, including Anna, look for jobs now. She's in the Netherlands, and as you can get with this kind of attitude, if she comes back to Russia, she'll have free accommodation and food for the next 10 years. So she's looking for postdoc or junior faculty. She is a mother of 3 living in the Netherlands. If you know somebody, talk to me and talk to her. We have this guy who did the metallicity measurements. He's just finishing the master's now and is looking for a PhD position, preferably in Europe. And Kirill, who some of you might have met here, is looking for a postdoc in France. And that's all. Thank you very much.
Thank you, Igor. So here are the numbers. If you take a disk, as you suggested, it's 335 kiloparsecs. At 300 kilometers per second, the rotation period is 10 to the 10 years.
Yeah, but
So my suggestion, we know that the satellites in the Milky Way galaxies occupy a preferred plane, for example, right? And so it may well be that it's not a virialized system, it's just
this is R200. This is the halo radius. This is not the disk. The disk radius is 150. So it's half of the Hubble time.
Half the Hubble time.
Okay, yeah.
But still, it will mean that only 2 orbits during the age of the universe.
So that's one of the puzzles. We were looking into this, and for us also the puzzle is this thing because it has a lower velocity. That's not on a plateau. So we suspect that that's a blob that is currently being accreted by the system. So it's still growing,
No, but we have a preferred plane of satellites, so you might be just observing a group of galaxies that has a preferred plane of orbits.
I think this one has more H1 than the entire local group. That's the point.
Okay.
Questions?
Other comments, questions?
What's the general environment of this? Is it part of a filament? Is it just isolated? Is there a cluster nearby?
This one, just for the record, this is the background stuff.
Yeah.
It's a group dominant galaxy. I would say you can call it a fossil group. Fossil group because it's way brighter than the second most brightest system in the around it. But it's generally a calm environment. So I don't know whether it's in the filament or not. We haven't checked. But it's definitely not in the cluster.
Yeah. Okay, and that's true for the other ones as well?
There are a couple that are kind of dense-ish, but not really. Nothing is in the cluster. Clusters destroyed this stuff.
Yeah. All this H1 has to come from somewhere.
Yeah.
Please.
Two questions. So, if it's a velocity gradient, can it be a cushion filament? And whether the disk and the center can be interlopers.
So, first of all, this is clearly a rotating disk because we fitted the full dynamical model into this one, into the H1 cube. It's just work in progress, so I didn't have time to prepare like nice presentation, and we're still trying to refine the details. This is also suggested by the fact that first of all you have this nice rotation curve that has much higher spatial resolution in the H alpha, unfortunately not going as deep, and also the disk has been already it has been evolving for some time because the gas is enriched. So, the metallicity is minus 0.35 dex, so it's slightly below half of the solar. If you expect it to be a filament, you would expect it to be much more metal poor. So,
Any other comments? If not, let's thank Igor for stimulating.
We're supposed to be Or should we allow all point of views from?
Your mic needs to go.
Igor, your mic.
Oh.
You can continue to speak.
no, the mic is here. So, yeah, you just turn it on like this.
Oh.
Yeah.
Is it on?
Yeah, now it's on.
Hello. Is microphone working? Okay, great. Oh, continue. Okay, great. Hello, everyone. I am Minjung Park. I also go by MJ. I'm a fourth-year grad student here at CFA, working with Charlie Conroy. And today I'm very excited to talk about star formation and quenching history of massive quiescent galaxies at cosmic noon, revealed by JWST deep spectroscopy. So star forming activity is one of the key properties of galaxies that distinguish two distinct classes of galaxies, of star forming versus quiescent galaxies. In the local universe, there is a clear color by modality showing that most massive galaxies are quenched red and that, forming this red sequence. And one of the important questions in galaxy formation is to understand how they are quenched and become quiescent. And many quenching mechanisms have been proposed over decades, and they can be broadly classified into two main processes with different timescales. So broadly speaking, processes involving directly removing gas from galaxies is thought to be rapid on a timescale of a few hundred mega years. And the other processes, like gas heating processes, are thought to be more slow on like a giga-year timescale. And in the local universe, many studies have measured the quenching timescales, and they found that local quiescent galaxies have a broad range of quenching timescales from rapid to slow, suggesting that multiple quenching mechanisms have been acting on local quiescent galaxies. On the other hand, at higher redshifts, at redshift higher than 3, only a few individual samples of massive quiescent galaxies have been spectroscopically confirmed. And because the age of the universe at such high redshift is very young, only a few giga-year-old, quiescent galaxies found at high redshifts are required to be quenched very rapidly. And to build up such high stellar mass, they are also expected to have intense starbursts to build up their high stellar mass. So this is one of the earliest massive quiescent galaxies that are spectroscopically confirmed at redshift 4.6. And the derived star formation history shows that these galaxies had experienced very intense starbursts followed by rapid quenching. And what about the redshift in between the low and high redshift? So the cosmic noon at redshift 2 is the epoch when the global star formation rate peaks. So majority of galaxies at these epochs are still actively star-forming. At this redshift, galaxy mergers are very frequent, so galaxies are actively growing. And the associated feedback processes, such as supermassive black hole feedback, is also thought to be the most active. Based on the popular rest frame UVJ color diagram distinguishing the quiescent and star-forming galaxies, we know that at this redshift, large fraction of massive galaxies are quenched. However, it is very expensive to get the IR spectra for rest frame optical for individual quiescent galaxies at redshift 2. So a lot of important questions about the quiescent population at cosmic noon still remain unanswered. For example, like how many galaxies are rapidly quenched versus slowly quenched? And what are their quenching mechanisms? And thanks to JWST, with its unprecedented IR sensitivity and multi-slit spectroscopy, we can obtain spectra of 100 objects simultaneously and have a full census of the quiescent population at cosmic noon. So in this work, we use the data from the Blue Jay survey, which is JWST Cycle 1 program, medium-sized program. And Zero Belli at the University of Bologna in Italy is the PI of the project. And we observe a representative sample of 150 galaxies at cosmic noon, the stellar mass down to 10 to the 9 solar mass, with JWST NIRSpec medium grading resolution that covers the full wavelength coverage between the 1 to 5 microns. And we used 2 pointings in the Cosmos field, and the observation was completed in December 2022. And I just wanted to highlight and thank to this wonderful Blue Jay collaboration. We had a group photo at a very familiar location. The NIRSpec deep spectroscopy reveals a very interesting rest frame optical spectral features. You can see very deep Balmer absorption lines and oxygen 2, oxygen 3, nitrogen 2, ionized gas emission lines. To understand the stellar population of the Blue Jay galaxies, we use Prospector, a SED model called Prospector, fully Bayesian stellar population inference code developed by Ben Johnson here at CFA. And this movie shows how the Prospector works. The stellar population model of a galaxy is described by a set of stellar dust parameters. And you can see that as we add more photometric points, the posterior distribution of the parameters get narrower and become the true value. And in this work, we fitted both observed HST and speech or IROC photometry and the rest frame optical part of the NIRSpec data. And here's our best fit SED model. And we can derive the star formation history from the SED fitting, which is basically the age distribution of stars in a galaxy. And we use the non-parametric star formation history model. And other stellar and dust parameters are also derived from the SED fitting. To select quiescent galaxies at cosmic noon, we plot all our Blue Jay galaxies in the plane of star formation rate versus stellar mass. And we selected 16 massive quiescent galaxies that are 1 dex below the star forming main sequence at redshift 2. For each of the massive quiescent sample that we have, we measured 2 important epochs in the star formation history. One is the formation epoch, which is when the galaxy formed half of its final stellar mass. And the other is the quenching epoch, basically when the galaxy is quenched. And we classified 16 massive quiescent galaxies into 3 different groups based on these 2 epochs. So the first group is as this, just like this galaxy. The first group includes galaxies that are early formed and quenched at very early epochs. And we also identified galaxies that are early formed but are quenched recently, and we named them as group 2. And the last group is galaxies that are formed very recently with intense starburst and then recently quenched very rapidly. And we identified almost equal number of galaxies in each group. And we find that among our 16 massive quiescent galaxies, 70% of them are recently quenched, and half of them have flat formation history with nearly constant star formation rate and then rapid quench. And then the other half had a major starburst prior to rapid quenching. To understand the quenching mechanisms, we studied neutral and ionized gas properties. So as shown in this one example galaxy presented in Bell et al. 2023, there are some spectral features that are not well reproduced by the best fit stellar model. For example, the sodium D absorption line. This is because the sodium D line can be observed by the intervening foreground gas. So the excess sodium D absorption line can probe the gas in neutral phase. And in this particular case, the excess sodium D absorption line is blue shifted, meaning that we are basically seeing the approaching side of the outflowing gas coming out from the galaxy. And in Davis et al. 2023, they investigated the excess sodium D absorptions in the entire Blue Jay sample, and they found a widespread agent-driven neutral outflows in massive systems, both in star-forming and quiescent galaxies. And in this work, again, for the three different galaxy groups that we identified, here I'm showing the excess sodium D absorptions for each of the galaxies in the groups. And the panels are color-coded based on the centroid velocity of the sodium D absorption line. So the green shows the sodium D line is the velocity, centroid velocity is consistent with systemic velocity of galaxies, and the blue panel shows that the sodium D line is blue shifted. And you can see that galaxies in group 2 and group 3 galaxies, group 2 and group 3 show more blue shifted sodium D absorption lines. And we also fitted 3 Gaussian components to the nitrogen 2 and H alpha emission line complex and measure the nitrogen to H alpha ratios. And we can see that recently quenched galaxies in group 2 and group 3 show neutral gas outflows probed by blue shifted sodium D absorption and ionized gas emissions with high nitrogen to H alpha ratios more consistent with the AGN diagnostics. And this all suggests that the AGN feedback drives multi-phase outflows, which leads to recent rapid quenching. So here I'm giving the summary of this work. In this work, we used the data from the Blue Jay survey, which obtained JWST or of 1,000 medium grading spectra of 150 representative galaxies at cosmic noon. And we selected 16 massive quiescent galaxies from this representative sample. We derived their star formation histories using Prospector and classified them into 3 groups based on how early and recent their formation and quenching were. And we found that 70% of the massive quiescent galaxies are rapidly and recently quenched. And we also saw that not all recently quenched galaxies have major starbursts prior to quenching. Half of them have flat formation histories with constant star formation rates before quenching. And to understand the quenching mechanisms, we studied the neutral and ionized gas and found that most of the recently quenched galaxies show neutral gas outflows and ionized gas emissions consistent with AGN diagnostics, and this suggests that AGN activity drives multi-phase outflows that leads to rapid quenching. Thank you very much.
Thank you, MJ. Did you see any galaxies that simply consume the gas that are not quenched as a result of feedback?
You mean the star-forming galaxies?
Yeah, they have some fuel of cold gas and they just consumed it.
Yeah, I mean, yeah. So the 16 quiescent galaxies are just a subset sample of the entire Blue Jay galaxy. So we definitely do see there are massive star-forming galaxies that are shipped too.
Okay. Yes? Oh, okay.
So are you able to estimate a duty cycle for the AGN given the if we could start to try to understand J cycles, at least this specific type of galaxy quenching as a function of redshift, because you have a set of cosmic news following.
Yes.
So, on that?
We haven't, I haven't looked at the duty cycle of the agent feedback, but I could only see the blue shifted, the sodium D neutral gas outflows only in the recently quenched galaxies. So I assume like if it was quenched like at early epochs, we wouldn't be able to see the ongoing outflows at the moment.
Igor?
Yeah, in one of the first spectra from Blue Jay, I noticed that you had a mismatch in calcium K line, which is sometimes considered as an, like, it might either be a problem with the star formation history, so you're missing old stellar population, or it's a line originating from the atomic gas of the line of sight, even though it's ionized calcium. So what's your take on this?
Ionized calcium is also observed by the intervening gas, so I think it's due to the absorption by the gas, neutral gas.
So it's like similar to
the sodium line. Yeah.
Any other questions? Please.
So I was wondering if the quenching mechanism was defined, are they any different in the early universe versus like more typical like later stages of evolution, or is there any special about these quenched galaxies?
I think as we go to like higher redshifts, because the age gets younger at higher redshifts, so quiescent galaxies need to be quenched very rapidly as we go to higher redshifts. So I think we will see like more quiescent galaxies that are quenched by ejective agent feedback that quench galaxies very rapidly. But at lower redshifts, we will see the diverse quenching mechanisms that act very slowly and also very rapidly. So yeah, but I think we would see more rapid quenching galaxies as we go to higher redshifts.
We need to move on. Let's thank you.
Thank you very much.
Okay, so hello everyone. Can you hear me well? Okay. So today I'm going to tell you something about what I'm working on in the lab, which are aromatic ices, and what I'm interested in to see how this degrades when exposed to UV. But why we care about aromatic molecules? Well, we care because we know that biology relies heavily on aromatic molecules, but also because we know that these are widespread in space. And if we start from the beginning, from star-forming region, recently there have been several detections of aromatic molecules, including simple hydrocarbon like styrene and indene, but also more complex molecules that include heteroatoms such nitrogen, and for example, benzonitrile is one of the most recent detections. And then if we look at the evolution of this star-forming region, we see the formation of protostar and slowly the formation of a protoplanetary disk. And also in this region, in these environments, is recently benzene has been detected. And this was a recent paper that showed detection of benzene in the inner disk of a dwarf star. And of course, the protoplanetary disk will evolve and eventually, slowly, will become a planetary system. And we know that at least in our solar system, aromatic molecules are everywhere. And I want to point out one of the most relevant detection, which is on Comet 67P, where during the Rossina mission, people were able to detect several aromatic molecules, including benzene, toluene, but also more complex, such as benzonitrile and phenol. So what we established so far is that gas phase aromatic molecules are everywhere, present at any stage during the star and planet formation. But what about the ice? Well, from laboratory experiment, we know that these molecules are very low volatility. That means that we expect them to condense, to freeze out onto the grain, and to live most of their life onto the grain. And if they are in the ice phase, well, probably the chemistry of this molecule will be more important in the ice rather than in the gas phase. And that's something that people have studied, and they've tried to see what kind of more complex molecule you can form starting from benzene ice. And so, for example, if you mix it with oxygen and irradiate the ice with UV, you will see the formation of phenol. But also, if you have a mixed ice of benzene with hydrogen cyanide, expose it to UV photon, you're going to form benzonitrile. So you see that the complexity of the aromatic molecule can increase in very simple ice condition. But what happens when this molecule is alone? Well, benzene, aromatic molecule, can absorb UV photon, and as such, they can also fragment down to smaller component. And in this study, people have looked at pure ice or diluted ice, but this time without including any reactive component in the matrix, but just a noble gases like argon. And what they saw is that the consumption of the initial abundance of the aromatic molecule is significant, especially when you have a diluted ice. So we wanted to start from this and start to explore a little bit more what this means, trying to extend this experiment to more complex aromatic molecules to see if the presence of a substituent on the ring could enhance or prevent the fragmentation of this molecule when exposed to UV. But also we want to see how much the environment in which these molecules are is important. That's because in space we expect them to be diluted, maybe with water, maybe with CO. And then finally, once we have an idea of what these parameters are, we can try to make calculate some implication for a disk environment. But how do we do this? So we step downstairs in Karin Zollberg lab, where there is an instrument that is called SpaceCat. SpaceCat is a stainless steel chamber that is kept at a very low pressure, ultra-high vacuum regime, 10 to the minus 10 torr, at the center of which there is a substrate which is made of CSI. And we are able to cool down the substrate to about 10 Kelvin, but still control the temperature between 10 and 300 Kelvin. Attached to the chamber, there is a gas line where we can make more or less complex mixtures that then will be delivered directly onto the onto the cold substrate to create ice by condensation, by direct condensation. Of course, to measure, to know what's going on in the ice, we need a detection device, and for this instance, we have IR spectroscopy. And during the experiment, we want to deliver energy in the form of photons, and so for that reason, we have a lamp that is a wide range lamp with a peak at around 160. So in a general experiment, we will prepare the mixture in the gas line, deposit onto the cold substrate, take an IR spectra to assess the situation at the beginning, start the irradiation, and keep taking IR spectra at regular intervals to see how the ice evolves. And at the end, we can have something that looks like this. So in the dark green, you see the pre-irradiation, the initial IR spectra, and in light green, you see the final one. Of course, there are many other measurements in between. But here, I'm also showing you what kind of matrices we are using. So we are starting with a pure molecule to see what happens when only the fragmentation of the molecule is allowed. We mix it with xenon, which has argon, is a noble gases, and so we don't expect any reactivity between the molecule and the matrix. And then we start to get more complex. CO, for example, is not something that fragments down in this condition, but it's something that could be part of the reactivity of your aromatic molecule. And then we have our two most reactive matrices, which is O2 and water, which after irradiation can form very reactive species such as oxygen atom or OH radical. And here we can see a few things. First is that the formation of CO2 and CO is pretty common, especially in the more complex experimental condition, but also that there are many other peaks that are forming, suggesting that something is changing. Whether this is more complex chemistry or simpler, the formation of simpler molecules is something that we still don't know. But for now, what we care is the main peak of benzene. And we want to see how much this changes as the photon fluence increases. And we can plot for each of the experiment all the measurement that we took, the IR spectra we took at the different timestamp. And since the intensity or the area of this IR band is proportional to the amount of material, of molecules that we have in the ice, if we integrate all of these curves, then we can make a plot in which we have the abundance of the molecule versus the photon fluence. And here you can see all the data put together in that format. So the first thing that I want to draw your attention to is at the pure. Again, we see that these molecules are not breaking down. The photolysis yield is 0% after at the end of our experiments. And to investigate this, we asked the help of our undergrad, Aurelia, who did the senior thesis with us in the lab and took care of this experiment. And what she did is she looked at molecules that are smaller than the original benzene and toluene molecule that I was showing before. And what she found is that the photolysis rate increases dramatically as the size of the molecule decreases. So if this is a size-dependent behavior, well, probably it's a mobility issue. Like the molecule, the fragments, the radicals are not able to move around the ice sufficiently. But if this is true, that means that increasing the temperature, we should expect the fragmentation to increase. And so we ran a couple more experiments with benzene at 100 Kelvin rather than 10 Kelvin. And yes, we see that even if so slightly, the photodegradation yield increases. So it seems that mobility is important. So now I'm showing the same set of data, but instead of dividing it by molecules, it's divided by the different matrix that I'm using. And what I want to point out here are a few things. So the first one, the first thing that we can notice is that in the O2 and water, we have a higher photolysis yield, let's say. So the more molecules get destroyed. And that's something that we can expect because, as we said before, these molecules are capable to react, to add additional reaction channels to the one available to the ice. And so we expect more of the initial material to be consumed. The other thing is that in each of these panels, we see that the behavior of the three molecules is very similar to each other. So it seems that our idea that maybe the presence of a substituent on the ring may be important for the behavior in this kind of condition seems not to be. But the third thing is how different is going from pure ices, undiluted ices, to diluted ices when the matrix is not able to react in any way, neither with the radical probing the chemistry or with the matrix itself probing the chemistry. And we can look at that in terms of mobility again. So if we have a benzene in a pure state, that's completely surrounded by other benzene. So when the photon arrives, it breaks down the fragment, and they cannot really move because the matrix is so stiff. So the only thing they can do is recombine and reform the original molecule, which doesn't give us any information in the spectra. On the other hand, when we have a smaller matrix constituent, the fragment will form, and now the matrix will kind of envelope this fragment and help them to find a different recombination match. This means that it is yielding a different molecule, meaning that we see the disappearance in our spectrum. So the smaller the matrix molecule, the higher the diffusion. So switching gear really fast into the disk, we want to see how what this means for a disk environment. So the first thing that we want to do is to derive the destruction cross-section from this experiment. And here we're just seeing the benzene in water because that's probably the most relevant condition. And we just use a first-order kinetics steady-state approximation, and we find the constant, which is about 3.3 to the minus 18 inverse centimeter. And then with the help of Jenny, we can use this number to see which area in a disk can be viable for the chemistry of this molecule. So from Jenny's model, we were able to derive the photon flux, and using the constant, we determined that there could be 4 different regions in a disk. The first one is a gas phase is the gas region where the molecule will be in the gas phase because everything is so warm and so close to the star. Then an aromatic photodestruction zone where the photon flux is going to be too high for this molecule to have a lifetime that is significant for the chemistry. And then a dark region where this molecule will survive forever, way too long than necessary, but also there will be not enough flux for them to react. And then finally, an aromatic ice photochemistry zone where many different reactions, whether to increase the chemical complexity or to fragment them down and then go for their way, can happen. And with that, I'll leave you with the summary.
It's beautiful to see the interplay of experimental physics and astrophysics.
Yeah.
Any comments, questions? By the way, if you want to visit the actual experiment, it's downstairs from the...
Yeah, and we can give you a tour anytime you like.
Any questions, comments?
Yeah.
Please go ahead.
What kind of product comes out of your benzene and water matrix?
So we haven't looked directly at the products yet, but we likely see formation of some phenol. But I haven't, that's the next part of the analysis. For now, we just focus on the destruction, but most likely some oxygen inclusion would be present.
Last question, go ahead.
Yeah.
If you go back a couple of slides, when you had the plots showing, another couple, the different species. Okay. So some, in some cases, all your three types are just the same.
Yeah.
Some are very different. In some, like two seems to go together and one in a different way.
Yeah.
What is your take on that?
So first of all, like I would think that at about a 10%, I think this one is 10% variation. It's not significant. Like there are so many aspects, so many uncertainty that these two values could be the same. So I will consider these two to be similar. For this one and for this one, we are actually investigating. This one seems to be an issue with, well, not an issue, something that complicates the problem, which is the thickness of the ice. It seems that this reaction are very sensitive to the thickness of the ice, which makes sense because the thicker ice will have different photon penetration, but we didn't expect to see this much at this regime. And so we are doing more experiments to see whether that depends. And same thing for this one. It could also be a thickness issue or thing.
Thanks.
Yeah.
Thank you, Elettra. Let's
Yep.
thank everyone.